Welcome students. This is our 8th lecture, and as part of the NPTEL MOOC program on handling healthcare survey data. In this week we are trying to understand how to go to the field and collect data. In this regard, I have already discussed with you regarding the very requirement for the field, like questionnaire, the like schedules, okay, and some pre-piloting aspects of the survey. In this lecture, we will be emphasizing on the most important aspect of the field is about sample size, and we know that sample size is important, not just in giving better statistical results. It also important so far as the budget is concerned, so far as the environment is concerned. So without delay, let's start discussing about sample size determination. The most common question we often ask is how large is our sample size? What is that size do I need? To get the answer, the researcher asks certain questions like how accurately do you need the answer? What level of confidence do you intend to use, and what is the expected result based on previous research? So, these three supporting questions will answer the first question about sample size. In the selection of sample size, we usually come across the following questions. What should be the size of the sample? How large or small should it be? If the sample size is too small, will it serve to achieve the objectives? Is it too large? Do we need to incur huge cost or resources? The sample must be an optimum size, and it should neither be excessively large or small. So, this is all about the introduction about sample size. Let us come to the discussion of what is that sample size. This is basically the number of individuals from whom we obtain the required information, and this is usually denoted by the letter small n. The capital N refers to population size. The size of our estimate bring some discussion about the population. Estimate from the sample, that is from the n, small n, leads to certain assimilation, certain approximation for the large segment, and that is why sample size matters. The inappropriate sample size can result in type 1 and type 2 errors. Like here we have given as population with in a design, and from there a sample is taken. Right, some samples are selected, but this sample size is correct enough or not is to be discussed. Will the sample be representative to this population unit which we have just marked? Will the sample be accurate enough? An optimum sample is one which fulfills the requirements of efficiency, representativeness, reliability and flexibility. So, efficiency and other things we are going to discuss now. The level of accuracy that we desire for our sample or for our research is an important determinant of sample size. So, level of accuracy gives better results. The qualitative research, the question of sample size is less important, especially when we have a certain target of observing qualitative information. In that case, sample size may not be mattering much, rather your different qualitative questions, the qualitative nature of observations are important. Like on this chart, we have marked sampling error and confidence level. When your confidence level increases in your result, you can assure that your confidence level is very high for your testing In that case, sample size requirement is higher. And when the sample error is higher, sampling error or between the gap of the standard estimate to that of your sample statistics, if that gap is higher, in that case sample size is all sample size also matters, but sample size reduces the sampling error. Okay, so it is inversely related. Some of the criteria to determine sample size, we have marked it here, like nature of universe. What about your nature of universe, whether it is homogeneous, whether it is heterogeneous. If your universe or your population where you are supposed to test from the sample, when you are looking at your population, if the population unit itself very homogeneous, probably you need not require more size, more sample size. Small sample size would be justifying enough. When it is highly heterogeneous, you require large sample size. Coming to the number of classes proposed, lesser groups or lesser classes as compared to many groups. Okay. If there are many groups, then many samples should be taken or large samples should be taken. When it is of smaller groups or lesser groups, you are supposed to take less number of sample. Coming to the nature of the study, whether it is very intensive or qualitative or general survey. In case of general survey, you are supposed to take large sample, but when it is very intensive, very focused, then you need to just take so many samples. So a couple of samples or very small size may actually give you justification. Then coming to the standard of accuracy and acceptable confidence level, whether it is high confidence level or low confidence level. Like as I just said, if you target for high confidence level, then of course you are supposed to take large size sample size as against the low one. Like if you wanted to test a consignment and out of that how many products are good or bad, you have simply taken some size randomly. If you are saying that your result is very confident at 99% or at 95% level or even any percent level, if it is higher, then you are supposed to take higher sample size. Regarding availability of finance, if it is there, if it is higher, then large samples result in increasing cost of sampling estimates. Or some other considerations are equally important, like nature of units you are supposed to take, size of the population, size of questionnaire, availability of trained investigators, the conditions under which the sample is being conducted, the time available for completion of the study. These are also considered while taking the sample. Now we are moving to the understanding of some basic statistical conceptions related to sample size and its calculation. So for sample size calculation, why it is necessary and where is it necessary? It is connected to hypothesis testing. Okay, so as we all know that we have a null hypothesis and we have one alternative hypothesis. Null hypothesis basically donated with H0 and H1 for alternative 1. For the null hypothesis, that says statistical hypothesis of no difference between in your testing. It is tested for its possible rejection under the assumption that it is true. So null hypothesis is considered as if there is no difference, or it is always true, or it is true. So if your test is going to reject it, then accordingly we can have some discussion. Like in the null hypothesis, it can be it shall be rejected or not rejected at certain level of significance. As against to the null hypothesis, we have alternative hypothesis. When null hypothesis is rejected, that means you are accepting your alternative hypothesis. The hypothesis representing the opposite of the null hypothesis, and is called alternative 1. So H0 and H1 are mutually exclusive events. okay, and accordingly we take testing. Now, there are some errors in the hypothesis testing. Those errors are called type 1 error or type 2 error. Type 1 error basically when we are rejecting the null hypothesis, when we consider that it is true to test any context you consider, and we simply say that it is true. Like for example, like the COVID, suppose you wanted to study the implications of COVID on rural economy and their nutritional level. The first null hypothesis in this context might be like the COVID has created no difference to the population so far as its nutrition status is concerned. So, the alternative will be yes, it has created differences. So, in that case yes and no. So, created difference may be positively, may be negatively. So, it has two tailed interpretation, two tailed direction. So, and one tailed when we say that you wanted to test that your COVID has positively affected the nutritional status. If that is your null hypothesis, then alternative will be it positively affected or influenced. So, now the error of basically the type 1 error is saying the error of rejecting null hypothesis on the basis of information collected from the sample, and when it is actually true. So, you are actually rejecting the null hypothesis when it is actually true, that is called type 1 error. Okay. So, why it is called type 1 error? That is also called denoted by alpha, and type 2 error is denoted by beta. Okay. So, or 1 minus alpha. So, what is that? Type 2 error is beta. Now, let us come to the first type 1 error, rejecting a null hypothesis when it is actually true. Like you said you wanted to test for a context, but your sample has given certain information. On the basis of that you are rejecting your population unit. Like for example, one inspector, food inspector has come to the place to a restaurant and or inspecting vegetable quality in a shopping in a supermarket or in a mandi. Now, the person has selected some sample. Based on the sample, the inspector is finding that the vegetable quality is not good. Okay. These are infected qualities, or there are certain problems with the vegetable. But in fact, your total sample, the total available vegetables in that market is in fact on the average is fine, on the average it is good. Your sampling unit, the response you have taken might have been erroneous, which might have given certain wrong signal or wrong estimates. Based on that you have rejected your population, that is entire mandi and its products are bad. So, that might be due to sampling error, that might be due to non-sampling error. We are going to discuss some of those things, but first of all when we are rejecting the null hypothesis based on your sample estimates, these are called type 1 error. The opposite is type 2 error, that is an error. Why error? When you are accepting a null hypothesis when it is actually false. Your sample might have given a correct result, but your total product are not right. Okay. In that case, that is called beta. So, the significance level is also is denoted by alpha, that is probability with which the null hypothesis will be rejected due to sampling error, though it is true. That is called alpha error or significance level. Okay. So, the margin of error, it is a random sampling error which is a likelihood of sampling results variation from the population. Okay. So, it is a random sampling error which is a likelihood of sample results variation from the population. Basically sampling error gives the standard deviation or the standard deviation of the sampling estimates and between the sampling estimates and the population. Okay. So, the standard deviation of the sampling distribution is actually called sampling error. Now, what are the catch in understanding the sample size? You can also click on this web link, you will be better guided. I will guide you here that how you can able to have these aspects, like what is your margin error, what is your confidence level, how big is the population, how do you believe the likely proportion to be included in the sample. First of all, margin error, if we set at 5% and your confidence level is at 95%, and if your population size is 10,000, then you with 50% proportion to be included, with a 50% probability of that sample to be included in your sample size is going to give you 383 number of samples. Small n can be calculated, and this is what is called 383, and that you can just test. I will clarify those concepts, confidence level, margin error and proportion, everything in my successive slides. Okay, so coming to this margin error and the sample size determination. When the margin error, your error in your calculation in that margin, if it is very less, that means when your margin error is very less, but is for sure you are supposed to take more sample size. Okay, sample size is higher. If it is just 2%, your margin error is 2%, you are supposed to take higher sample size. When you are taking less size, you may compromise with a margin error. Okay, and when your sample size is increasing, your distribution is becoming more elliptic. Okay, it is symmetric, normally distributed, but when sample size is lesser, it seems your alpha margin is higher, or your margin error, these are called alpha regions, these are expected to be higher. Okay, because the rejection region will be higher, but here when it is more of elliptic, your margin error in its extremes are very less. Okay, so we can find it out in our chart. Some alternative scenarios to calculate sample size is that where sample size is 100, then 100 to 100 and 10,000. Your margin error would be expected to be lesser, is expected to be lesser. Okay, this is again very lesser. On the contrary, when your margin error is higher, you may supposed to take less sample size. Similarly, some decisions taken regarding confidence level, when your result are expected to be very confidently building, or your result is quite impressive, is quite confident, then you are supposed to take more sample size. And when the population size is much higher, you are also supposed to take when this is higher, you are also supposed to take more sample size. Now similarly, when your sample proportion is higher to some extent, like with a sample proportion of 10%, you are taking certain n, but what is that you need not decide it, depending upon population size. Once you enter the population size, so many indicators are derived based on that website, which we have just shown. When your proportion is 25%, you are supposed to take more. When your sample proportion is becoming much higher, then probability, that is the probability of success, is higher, p is higher, and q is lesser, much higher than that of q. Probability of failure, in that case you need not take more sample. Okay, some of the samples or the pure sample can also give you better result. Now we are clarifying some concepts like margin error and confidence interval. We are often confused, researchers are often confused about these two concepts, like margin error. it tells you how many percentage points your result will differ from the real population unit or population value. Okay. So, how it is differing from how your sampling results, sampling points or sampling estimates are different than that of your population estimates. Okay. The margin error is in fact the range of values below and above the sample statistics in a confidence interval. So, from a confidence interval it defines your margin error, like a 95% confidence interval with 4% margin. 95% confidence interval with 4% margin error means your statistic will be within 4 percentage points, okay, of the real population value with 95% of the time. So, in all 95% of time if you test it, your result will be from the mean value will be varying by 4% plus or minus. Okay. So, this is where confidence interval and margin error work out and gives the right guidance in testing. The confidence interval is a way to show what the uncertainty is with a certain statistic. So, but the uncertainty, but it gives a is a lower slab and upper slab in the pool or in a survey. Okay. One example we have cited here in a like in a pool might state that there is 98% confidence interval of 4.88 and 5.06. That means this 4.8 till 5.26, that indicates your range, upper limit and lower limit, because of the because of the margin error. That means the poll is repeated using the same technique 98%, since 98% confidence we have taken. So, if this is repeated, this poll is repeated 98%, the result will be varying within the limit of 4.88 to 5.26. Okay. So, it will fall within the interval between 4.8 to 5.26, and that will be repeated for 98 percentage of the time. So, that means error is very minimum, and error gives a range of your result. The idea behind confidence level and margins of error is that any surveyor pool will differ from the true population by a certain amount. However, the confidence interval and the margins of error reflect the fact that there is no room for error. Okay, these gives no room for further error. So, although 95% and 98% confidence with a 2% margin error might sound like a very good statistic, room for error is built in, which means sometimes statistics are also wrong. So, this indicates though 2% errors are mentioned, and then we are saying that this result is going to be almost 100 times confidence. So, this always gives certain room for errors, and that error is pretty minimum. So, that is why statistics give a better direction for taking decisions. A poll might report that certain candidate is going to win an election with 51% of the vote. If they are saying 51% of the vote, that means the confidence level, if the confidence level is of 95% and the error is 4%, that means loss 51, 5 plus 4 and 5 minus 4. So, that will be, if error mark is given, that means your 51% margin increase in vote, or the vote vote percentage, if it is 51 for a candidate with an error of 4%. Okay, let us say the poll was repeated using the same technique with 95 times. Okay. So, that means there will be an error of plus 4 or minus 4. So, that will vary your result with 51% vote, you are going to get it maybe of 47. When you are saying 51% vote a candidate is going to get, that may get 55% or may get 47%. Now, of course, not below to that. That means we can guess about the product or about the candidate in an election better. Similarly, while calculating margin of error, there are some steps involved. Those steps, like margin error can be calculated in two ways depending on whether you have parameters from a population or statistics from the sample. Margin of error is calculated with the critical value times standard deviation of the population. Okay, if we are calculating for the population. So, critical value, the margin, the critical value limit, once we have defined times is standard deviation, if you give it, that gives us margin error. Similarly, for the sample critical value and its standard error. Okay. Second, for the first step, how to find the critical value, who gives the critical value. Okay. So, first of all, we say critical value for the sample case or for the population. Let us understand critical value. The critical value is either a T score or a Z score. Okay. Z value, Z tabulated value, or the T score tabulated value. If you are unsure, then we can see the T score table or the Z score table. In general, for small sample sizes, usually less than 30, one sample size is less than 30, or when you do not know about the population standard deviation, population, about the nature of the population and standard deviation, when you do not know, usually we do not know, and in most of the cases we apply T score, T table. Okay. Otherwise, if it is correctly known, then Z score can be applied. Second step, find out the standard deviation or the standard error. These are essentially the same thing. Standard error is used for sample and standard deviation for the population unit. You must know your population parameter in order to calculate standard deviation. Otherwise, calculate the standard error from the sample. Okay. Third step is to multiply the critical value. That critical value, once we have determined here, we may multiply with the standard error. That will give us the margin error. Okay. For example, if critical value is 1.96, 1.995 and 95% Z score and value is 1.96. If it is 1.95 and your standard error is of 0.019, then 1.95 times 0.019, that boils down to 0.03. So, 3.7% is your standard error. So, further details you can follow this link I have appended in this page. Second one is how to find the probability value of Z with the Z table and the T value with the T table. I have put some references here for your understanding. Like you can use the Z table to find a full set of less than probabilities for a wide range of Z values. Okay, like once a limit is mentioned, from there what is the probability of that Z value. So, to use the Z value to find the probability for a statistical sample with a standard normal Z distribution, we need to follow those following steps. First step, we need to need to go to the row that represents the ones digit and the first digit after the decimal point, like the tens digit of your Z value. I will show it to you by example. So, then we go to the column that represents this second digit after the decimal point, then and of your Z value. Third step is intersect the row and column from 1 and 2. This result represents probability of that Z value with that limit. Okay, and rest you can follow from this, and I am just going to show it here. Like on this table, the one sample Z table, but this Z table is plus the positively skewed one is given the value Z value which is higher from 0 is given. So, like if you are interested in finding out the probability of the Z value at 2.13, okay. So, using the Z table value we can find out, like first of all you need to check with 2.1, okay, from the row which where is 2.1, we can mark it first here. then the second digit after decimal, that is 0.03. 0.03 you can mark it 0.03 over here, and now with the intersection we get a value. This is going to give us 0.9834. Okay, so basically it says what is the Z value. Z value with let it be 2.13. 2.3. What is the probability value over this region? Okay, so in this case we have derived the tabulated value. The critical value is at 0.9834. So now noting that the total share under any normal curve, that is the standard normal curve, here we have defined Z value is the standard x minus mu by standard deviation, x minus mu by standard deviation. Okay, this is what is mentioned. So now now it follows with the Z value less than 2.13, and if this is of 0.0, this is the probability value is 0. The cumulative probability value is of this one. The rest of the area should be 1 minus of this 1 minus of, so 1 minus 0.9834. Okay, so this should be added to 1. Therefore, phi probability of Z greater than that of 2.13 should be 1 minus of P of Z of less than 2.13, which is equal to this, and this probability cumulative value should be of this much. Okay. Now let us move to the T distribution. T table I have presented here for your reference. Usually the researcher who just started reading statistics at the undergrad level, they might get confused in reading the tabulated values. So reading the T distribution, we require three things. First one is degrees of freedom, then number of tails of the T test, whether it is one tail test or two tail test, and third one is the critical limit, the alpha level. Okay, the critical limit that is at 1% or 5% or 10%. So that has to be mentioned. Like in this example, we have said we have given in the table the figures are given one tailed, two tailed, and its degrees of freedom. First of all, like in a study, like a researcher requests 20 subjects for a study and conducts a one tailed t test. It is clearly mentioning one tailed t test for a mean using an alpha level of 5%. Okay, that is 5% alpha level, critical level, and the researcher requests 20 subjects for a study. Once she conducts her one tailed t test and obtains a test statistics T, what critical value should she compare T to? Okay, so what is the critical value or the tabulated value of T? For this 20 subjects are there, and our degrees of freedom is with one assumption, that is lost our freedom of testing. So 1 degree of freedom is deducted out of this. So degrees of freedom is actually 19. In this case is 20 minus 1. So we are straight away going to check 19 here on the row. The problem also tells us that she is conducting a one tail test. So if it is one tail test, we have to compare these figures, these p limits, the alpha level, and it is said that it has to be at 5% level. So the 5% level is marked here. Now the intersection is defined to be identifying 1.729. Okay, so T value, the critical value as per the T is at this. Now what should we do? One decision we usually take, once your estimated statistic is higher than that of the tabulated value, that means we are not accepting the null hypothesis. That means we are rejecting our null hypothesis. That means that variable is significantly differing to the assumption. Okay, so accordingly we take decisions. So, final call on this is whether t test or j test. Like if we know our population deviation, population standard deviation, then obviously we will go for j test, and if you do not know, then we are supposed to go for t test. Once we know our standard deviation, then second call is what is the sample size. If it is 30 and lesser, if it is greater than 30, then if it is yes greater than 30, we will use Z table, else it is of T table. Now, there are approaches for determining the size of the sample. The approach based on precision rate and confidence level. Okay, to specify the precision of estimation and desired, and then to determine the sample size necessary to ensure it. We require mathematical solution and frequency used techniques. The limitation, it does not analyze the cost of gathering information. Okay. So, some of the approaches are based on Bayesian statistics also. I am not going to the depth of it, but just to give you certain guidance, minimum guidance, because of the fact that we are not going to apply it. Some approaches uses Bayesian statistics to weigh the cost of additional information against the expected value of the additional information, and it is theoretically optimal. Okay, it is seldom used because of the difficulty involved in measuring the value of information. So, it goes by understanding prior probability distribution, likelihood of the observation, and posterior or probability distribution of the events. So, that is why this is hardly used. I think I should stop here. I will start with the the determination through the approach based on precision rate and confidence level, and to the next class. Okay. Let me stop here. I will continue from the next class and clarify the exact sample size. Okay.